Okay, hello everyone, and welcome to our first demonstration example where we will be discussing a linear magnetics simulation. The problem the setup we are considering is depicted here on the right, where we have three regions: an air region, core, and a ring region. And this ring region is supplied with a constant magnetization. Respectively, in our case, it's a constant prescribed magnetic flux density. And we can define different core materials. And of course, this is an axisymmetric setup. So the z-axis is depicted here, the r-axis, and we're using an axisymmetric formulation of Maxwell's equation, or of the magnetostatics equation. Yeah, instead of showing you the slides, I would say we do the live coding or live demonstration. So you find all the necessary files on Teachcenter. You can download them, put them in your share folder, and access them. So the first example is called Perm Magnet Ring. So we enter this directory and you'll find two different journal files. So let's discuss both journal files. Since last semester I ran a bit short on discussing the trellis meshing process. I will quickly repeat that now. Okay. This was not what I wanted. Stop that. Okay. Now we open the editor and load the first journal file, the variant 1, which is kind of a bottom-up approach, where we first define all the vertices of the computational domain. Then we connect the relevant vertices with lines or curves, and then based on the curves we define surfaces and assign region names to these surfaces and node sets for the boundaries, which is a type of setup or hierarchical setup which might be suitable for scripting. So you can define variables in such a way you write this hashtag and the curly bracket defines the variable name. In this case, the only variable we are using is the variable called size, and which is used later on here in line 69, where we define the mesh size, where we actually use this variable. But in the same way, you can also define variables that with your node or with your vertex coordinates, and you can put these variables in here instead of the values, and you can vary these variables in a script, for example, and perform the meshing in a scripted way. So this bottom-up approach, first define the vertices, then curves, surfaces, and if you have 3D, then later on volumes, is very suited for scripting. Okay, so now that we have executed the first 48 lines, we have obtained our computational domain consisting of three surfaces: the air surface, the ring surface, and the core surface. The next step is, or the next necessary step to actually, yeah. Yeah. Yeah, yeah. Yeah, this is actually the second approach I wanted to show you in the Variant 2 journal file. So I will come to that in a few minutes. Yep. So in order to be able to call these surfaces with CFS, so to assign a material and to assign a prescribed flux density and to assign a material or to assign boundary conditions, we need to assign so-called blocks and node sets to these surfaces, which is done here in line 50 to 60. So if we execute these lines, we assign, for example, the name air to the surface with the ID 3, and ID 3 is this air domain. So if we check these blocks here, we have three regions: the air region, the magnet region, which is the ring region, and the core. So these are our kind of volume regions, and then we need node sets, which are the boundaries of our domain. So we have these vertical, I hope to see that in orange, these vertical lines here, and these horizontal outer boundary lines, and they have the name vertical and horizontal, so we can call them via the XML file. Okay, next step is to merge the surfaces and curves. So if we perform the meshing right now, we would get a non-conforming mesh. So this would result in hanging nodes. But we don't want to have hanging nodes, so we merge the surfaces and lines, and then we can execute the mesh command. Okay, take some time, and then we can perform the meshing. We define a size of the elements in every region, which is a constant size that we predefined at the beginning with this size variable, and perform the meshing with mesh surface all. Then we simply need to export this mesh as a CDB file. So this was the last step, and we can read this CDB file with OpenCFS. Okay, so this was the first approach to generate meshes, kind of I call it bottom-up approach. And the second approach, as Timon mentioned, is kind of the more intuitive way to perform the geometry. So let's reset everything. This was actually, I generated this journal file by copying the commands from the command line. So I was choosing, the first thing I wanted to do is create a rectangle. So I clicked here on the geometry tag, create a geometry. I want to create a surface. I can either define boundary curves, or I can define the length and width of the rectangle right away. So in our case, the width should be 0.025 and the height 0.03, and it should be in the set plane. Okay, apply, and we have our surface. So now we need to move this surface to the correct coordinate. In our case, we move it 0.0125 meters. So these are SI units in X direction, which can also be performed via the GUI. So you click here, transform geometry, transform surfaces, and we want to move this surface. So we want to move this surface to a distance x 0.0125, click apply, and we get the command that we simply need to copy into our journal file. So this is a more intuitive way, like a hybrid way to use the GUI and copy the commands, copy these commands to your journal file. So then you can also script this journal file, but you have all the benefits of having it in a more intuitive description. Okay, and so on, we perform the generation of the other two surfaces, move them to the correct location, and here they are. Now the problem is they are overlapping each other. So the next step is to cut out the ring and the core section from this air surface. And you can again do this by clicking here on perform Boolean operation, surfaces, and subtract. Then you can define the source surface and the surface you want to subtract, which is done here with these commands. So these 4 commands cut out the ring and the core section from the air domain. And in order to perform a hexahedral meshing, in hexahedral in 3D, in 2D, we want to mesh it with simple rectangles or quadrilaterals. We need to cut the air volume in Y direction and in X direction, which can be done by or via this webcut commands. These 4 commands result in the following geometry setup. Okay, then we have a meshable geometry. First of all, then we need to merge them again and perform the same meshing commands as we did in the first journal file and export the CDP file. So this, I personally prefer this approach over the first approach, the hyper-hierarchical approach, because it's simply more intuitive. Okay, so we have our geometry as a CDP file. We can close Trellis and have a look at this XML file here, the Magnet Nodal 2D Linear. So in order to do that, we enter Eclipse. So for those of you who are not in the exercise, I have provided a command that should activate this Eclipse command on Teach Center. So you should simply execute this command in the terminal, close the terminal, open a new one, and then this Eclipse command is available. Okay. Click launch. Okay, so in your case, it will look a little bit different because you will not have this XML example folder here. So you simply need to right click here in the empty space, which is not working for me right now. Okay, if you right click, go to new folder, and you can simply add your share folder. Click on advanced, link to alternate location, and browse to your share folder. So to home, share. Simply choose this directory and add it. I don't need to do that because I've already added it beforehand. And navigate to the demonstration directory. Then there you find the magnet nodal 2D lin XML file and open it via double clicking. Okay, how does the XML file look like? The first few lines, as you already know, is the header. So it defines where the XSD scheme is located, and this XSD scheme is simply needed to have this code completion available. So if you maybe enter a new line here and open this bracket, then you get suggestions of what is available. So in this case, it gives you suggestions for the available input formats. So with OpenCFS, we can read CDB files, CGNS, HDF5, and so on files. In our case, well, for this semester's session or class, we will only be importing CDB files. Just wanted to show you how this code suggestion or code completion is working. And if you are inside of such a tag and you want to know if there are any more attributes available, so this, for example, is called an attribute, simply click somewhere in between and click Control or type Control plus space, and then you get available attribute suggestions. This comes in quite handy. You can also do this here on the right. If you click here, right click here, add, material data. Yeah, it's freezing again. So stick to the control space. Okay, then we define our material file. As you already know from last semester, this material file, okay, let's use this one, it should be the same because it takes forever to open. Here we define the different materials for the PDEs we are solving. So in our case, we have, or in this material file, we have defined 1, 2, 3, 4 materials, so copper, aluminum, iron, and air. And we need to define the material properties for the specific PDEs we're solving. So in our case, we're solving a magnetic PDE, so we need these magnetic material parameters, which are the electric conductivity and the permeability. In our case, the magnetostatics case, we wouldn't even need the electric conductivity because it only depends on the magnetic permeability. And maybe I've taken this material XML file from another simulation where we also wanted to simulate the acoustic propagation. So I've also defined the acoustic material properties here, which we do not need, just to show you that we can define the material parameters for different PDEs. Okay, so in our case, we will be using the air material and the iron material for the core region. This already brings me to the domain section, and in the domain section we define which regions we're using from the mesh file, and we assign the materials to the specific regions. Okay, then comes the most important section, this sequence step section, where we first of all define the analysis type. And we have several analysis types available. In this demo example, we're only using a static analysis type, and combined with a magnetic PDE, this results in a magnetostatic PDE that we are solving. So in this PDE list tag, we define the magnetic PDE, we define the regions where we want to solve the PDE, the magnetic PDE. We define the boundary conditions, which are in our case flux density and flux parallel boundary conditions. This flux density is not really a boundary condition since we're defining a constant flux density, so we're prescribing a B field in the magnet domain, which is in the PDF is the ring domain here in this darker gray color. We define a constant magnetization in z direction with a value of 1.2 Tesla in this case. Okay, so this goes on the right hand side of our PDE. Then we define actual boundary conditions. Yeah. Yeah, because we don't want to interfere with the prescription of the magnetic flux density, because if we had a mu defined here, so if we assign a permeability unequal to the vacuum permeability, we would need to scale this value that we are prescribing. That's the reason why we really want to have this 1.2 Tesla in our ring domain or in our magnet region. And if we assigned an iron material to that, it would result in a different magnetization, in a different actual magnetization than we are prescribing. So you can try that out by assigning iron material to this magnet domain and observe what happens. Yeah. So these flux parallel boundary conditions simply mean, well, I will show you in a few minutes in ParaView, simply mean that the B field lines, so the magnetic flux density field lines, shall be parallel to the vertical and horizontal boundaries. Okay, and in this section here, in the store results section, we define the results that we want to output. So we want to output the magnetic flux density, of course, the magnetic field density, and the magnetic vector potential. So as you probably heard in the lecture of Professor Kaltenbacher, the actual quantity we are solving for in a magnetic simulation is this magnetic vector potential. Okay, so this is the XML file, and now we can proceed with simulating this XML file or executing it. Therefore, I open another tab, check if I'm in the correct folder, which I am, and you can type CFS and the name of the XML file you want to simulate. So I want to simulate this XML file, click enter, and CFS is simulating it faster than I can explain what it's doing. So this run took 1.7 seconds because it's not a big problem, and we can investigate the actual field by entering ParaView --MESA. We have to do this --MESA because of some graphics issues in the virtual machine, and then we navigate to the results HDF5 folder, which was created in this by executing this run command or the CFS command. This produces this results folder, and the result file is located in this results HDF5 folder and has the same name as the XML file we are simulating, with the difference of this extension. So it has the file name .cfs instead of XML. I hope this does not take forever to open. So this CFS file format is actually a simple H5 format, simple HDF5 file format. We simply renamed it to CFS to know that this result comes from an OpenCFS simulation. Okay, then it did not open it. I don't know why. So we navigate to the results folder and open this file. Okay, now we have loaded the result file, and here we can define which regions we want to read. So in our case, we are not interested in the boundary regions since they're only lines. So we uncheck the horizontal and vertical region. We only want to investigate the solution in the air, core, and magnet region. Click apply, and it's loading the result. And in this flyout menu here, we can define which region, or we can choose the different output results that we want to investigate. So in our case, maybe let's first have a look at the magnetic flux density. Yeah, looks kind of realistic. You can't really interpret much out of this plot, because this is just the magnetic flux density magnitude plotted. So the magnetic flux density, the B vector, is a vector, and what we've plotted here or represented here with colors is simply the magnitude of the vector. You can, of course, look at the different components, the RNZ component of this field via the color mapping, but the more engineering-like approach is to visualize the vector field as an actual vector field with arrows, and this can be done by clicking here on this glyph icon. Define an orientation array. So we want to orientate these arrows according to the magnetic flux density, and click apply. Okay, we see large arrows. We want to make them a little bit smaller, which can be done here with this scale factor. Let's decrease the size a little bit. A little bit more. And the color is chosen, the color of this vectors is chosen as the VTK block colors. So VTK is this output mesh format that can be read with ParaView. We don't want to color it according to these block colors. We want to color it, we want to have a uniform coloring, so we just enter this solid color, and then all the vectors are colored homogeneously. Okay, so this is the resulting B field. If we want to look at the actual solution quantity, which is the magnetic vector potential, we go back to, or we click on this result here and check the magnetic potential, which is the magnetic vector potential. What is worth noting at this point is that you see the difference of icons for the magnetic flux density, which is represented with like this hexahedral here, and the magnetic vector potential represented with a dot. And the difference is that this magnetic vector potential is actually a nodal quantity. So so every node, if we're considering first order ansatz functions, basis functions, no higher order stuff. If we only have lowest order ansatz functions, then every node of the mesh has 1 degree of freedom, and this degree of freedom is the magnetic vector potential. So this is represented by this dot here. It's a nodal quantity. And the magnetic flux density, the B field, is, I think you already heard that, is the curl of A, the curl of the magnetic vector potential. So it's a derived quantity. There are derivatives involved, and whenever you want to have a derivative of a nodal quantity, this derivative is defined in the volume. And in this case, the volume is actually the surface area of an element. So the flux density is assigned, or is constant in every element, as you see here when we zoom in, since it is a derived quantities based on the four quantities at the nodes of the magnetic vector potential. And the derivative is computed, and this derivative is the magnetic flux density. If we take a look at the magnetic vector potential, you see a different picture. You see a much smoother picture, and the reason for that is that ParaView automatically smoothens nodal values. So in this case, every node of our mesh, which you can visualize by clicking on this flyout menu here, surface with edges, you see the mesh, and here every node has a different colors, a different value, which are the degrees of freedom, the magnetic vector potential. And yeah, so this is the actual result and the visualization in ParaView. You can also, you can, maybe another description, the magnetic flux density, the B field, you can see here the arrows are located in the center of every element. So the vector is the curl of the magnetic vector potential. Okay, so this is it, what I wanted to show you regarding the first demonstration example, the linear magnetics demo example.